You can use the Floyd-Warshall algorithm to find the shortest path between all pairs of nodes in a graph. So to see how to use this algorithm, let's jump right into an example. Let's say we have this graph here with nodes A, B, C, and D, and we want to know what is the shortest path to get between each pair of nodes in the graph. To solve this using the Floyd-Warshall algorithm, we first create a distance matrix and a path matrix. Now, to fill in the values of this distance matrix, here's what we do. We ask ourselves, what is the distance from node A to node A? Well, from any node to itself, it's just a distance of 0. So from node B to node B, that's also a distance of 0. So what we'll notice is that in this initial distance matrix, all of the values along the diagonals are 0. Then we ask ourselves, okay, what's the distance from node A to node B? So to figure that out, we just see, is there a direct edge from node A to node B in the graph? And we can see that there is, and it has a distance of 1. So to go from node A to node B, that's a distance of 1. Now to go from node A to node C, we can see there is no direct edge from node A to node C in the graph. So initially we'll just say that this distance is infinity. And then to go from node A to node D, there's also not a direct edge in the graph going from A to D, so that distance will also be infinity to start with. And we'll repeat this process to fill in the rest of the distance matrix. Then we need to fill in the path matrix. So this is a matrix that shows which node most recently led to the shortest distance between one node and another node. So for all of the diagonals of the path matrix, we'll just put a dash, because to get from one node to itself, there is no previous node. Now if we consider to go from node A to node B, what was the node that most recently led us from A to B? Well, that would just be A, because we went directly from A to B. So we'll put an A right here. From A to C, we saw that currently there is no edge that leads us from A to C, so we'll just put a dash there as well. And from A to D, there's also no current path from A to D, so we can also put a dash right there. And we'll fill in the remaining rows in this matrix in a similar manner. Okay, so these are known as our initial distance and our initial path matrices. If we want, we can put a little sub-zero here to indicate that these are our initial matrices. Now what we're going to do is update these matrices by going through each node in the graph. So for the first time that we update the distance matrix, we'll ask ourselves if we can force ourselves to go through node A for each of these paths. So for our first update to the distance matrix, we'll call it distance matrix sub 1 and path matrix sub 1. What we're going to do is try to force ourselves to go through node A in this particular iteration. So because we're going through node A, the row and the column values for row A will not change. So we can just fill in those values. And the distance from each node to itself will remain 0. So we can go ahead and fill in zeros for all the diagonals. Now we just need to fill in the remaining empty cells. So to go from node B to node C, currently that shortest distance to go from B to C is -2. But here we want to ask ourselves, what if we force ourselves to go through node A? So can we go from B to A to C? Would that produce a shorter distance to get to C? Well, in this case, we can see that there is no direct edge from B to A. So in other words, that distance from B to A is infinity. And then from A to C, there's also not a direct edge, so that would be infinity plus infinity. So is infinity plus infinity smaller than the current shortest distance from B to C? No, it's not. So we're not going to update this value. So in other words, we'll just keep that as a -2. So in other words, trying to go through node A did not produce a smaller distance. Now if we consider from B to D, the current shortest distance is -1. So again, we ask ourselves, what if we force ourselves to go through node A? So from B to A to D. Well, again, there is no path from B to A. So the distance from B to A is infinity. And then from A to D, there's also not a path, so that's infinity plus infinity. So obviously this is not smaller than the current distance from B to D. So we'll keep that as a -1 as well. All right, now let's move on to the next empty cell. So from C to B, the current shortest distance is infinity. In other words, there's not a path from C to B. So now we ask ourselves, what if we force ourselves to go through node A? So from C to A to B, does that produce a shorter distance? So from C to A, that's a distance of 3, and from A to B, that's a distance of 1, for a total distance of 3 plus 1. So is 3 plus 1, which is 4, is that shorter than the current distance from C to B? Yes, it is. So we're going to update that value and make it a 4. So we'll write a 4 right here. Now to go from node C to node D, currently the shortest distance is 2, but what if we force ourselves to go through node A? Well, from C to A, that's a distance of 3, so 3 plus from A to D, that's currently a distance of infinity. In other words, there is not a route from A to D right now, so that would be 3 plus infinity. So is this shorter than the current shortest distance of 2? No, it's not, so we'll leave the 2 in the distance matrix. And moving on to the next empty cell, from D to B, the current shortest distance is 5. But what if we try to go through node A? Would that produce a shorter distance? So from D to A, that's infinity. There's no current route from D to A. So that would be infinity plus, if we went from A to B, that has a distance of 1. So plus 1. So is infinity plus 1 any shorter than 5? No, it's not. So we'll leave 5 in the table. And then lastly, to go from D to node C, that current shortest distance is infinity. So can we shorten that by going through node A? Well, from D to A, that distance is infinity. And from A to C, that distance is also currently infinity. So is infinity plus infinity any shorter than infinity? No, so we won't update that value yet. Now, for this particular iteration, we'll notice that there was only one update that we actually made, and that was going from C to A to B, which produced a distance of 4. So when we update our path matrix, it will be the exact same matrix, except from C to B, the most recent node that took us to node B would be A. So here's what that looks like. So again, the only update that we actually made in the path matrix this time was just putting an A right here. Now what we're going to do is repeat the process, but now we're going to try to go through node B. So I'll go ahead and shift these distance and path matrices up and make room for a new distance and path matrix. Okay, so now when we update this next distance matrix, we'll call it distance matrix sub 2, we're going to ask ourselves, can we force ourselves to go through node B to find a shorter route between each pair of nodes? So because we're going through node B, we're just going to fill in the column and the row values for B, since those won't change. And we can fill in zeros for all of the diagonals of the distance matrix as well. Now we just need to fill in the remaining empty cells. So currently, to go from node A to node C has a distance of infinity. Can we find a shorter route by forcing ourselves to go through node B? So in other words, can we go from A to B and then from B to C? So from A to B, that's a distance of 1. From B to C, that's then a distance of negative 2. So that total distance is 1 plus negative 2, which is negative 1. So obviously 1 plus negative 2, this is shorter than the current shortest distance of infinity. So we'll go ahead and update that value. So that's a value of negative 1. Now in our path matrix, we'll update this value to get from A to C. The most recent node was B. So we can put a B right here. Then we'll move on to the next empty cell. So from node A to node D, the current shortest distance is infinity. But what if we force ourselves to go through node B? So if we go from A to B, that's a distance of 1, and then from B to D, that's a distance of negative 1. So 1 plus negative 1 is 0, which is shorter than our current distance of infinity. So we'll update that value to be a 0. And in our path matrix, from A to D, previously there was no route, but now we can fill in a B, since B is the most recent node that led us to the shortest distance from A to D. Alright, now our next empty cell is from node C to node A, which currently has a shortest distance of 3. So what if we go through node B? Could we find a shorter path? So from C to B, that currently has a shortest distance of 4. And then from B to A, that distance is infinity. So is 4 plus infinity less than 3? No, so we won't update that value. Then we'll move to the next empty cell. So from C to D, the shortest distance is currently 2. But what if we force ourselves to go through B? So from node C to node B, the shortest distance is currently 4. Then from B to D, that distance is negative 1. So we would have 4 minus 1, which is 3. Is that a shorter distance than 2? No, so we won't update that value. Then if we consider the next empty cell, so from D to A, that distance is currently infinity. But what if we go through node B? So from node D to node B, that has a distance of 5. And then from B to A, that has a distance of infinity. So is 5 plus infinity shorter than infinity? No, so we'll leave it as infinity. So we won't update that value. And then if we consider the last cell, from D to C, the current shortest distance is infinity. So what if we force ourselves to go through node B? So from D to B, that currently has a distance of 5. Then from B to C, that has a distance of negative 2. So 5 plus negative 2, that's 3. So is 3 shorter than the current distance of infinity? Yes, it is. So we'll update that value in the table and make it a 3. So we made an update right here. So in our path matrix, we can put B as our most recent node that we went through to go from D to C. Now we can just go ahead and fill in all the other values in the path matrix using the previous values, since we didn't update any of those values. So this is our updated distance matrix and path matrix. So I'll go ahead and shift these ones up and make room for the next matrices. Now for this next iteration where we create distance matrix 3 and path matrix 3, we're going to try to force ourselves to go through node C to see if we can find any shorter paths between each pair of nodes. So to save a little bit of time, I'm going to go ahead and fill in the values for these updated distance and path matrices, and I'll highlight the ones that actually had updates in red. Okay, so in this iteration, we make 2 updates to the distance matrix. So we find that the distance is shorter to go from B to C to A, which has a distance of 1. If we check out our graph from B to C to A, that distance is 1, which is shorter than the existing distance of infinity. And similarly, we found that it was shorter to go from D through C to A, and that had a distance of 6. And if we check that out on the graph, to get to C, we went from D to B to C, and then to A. So that distance turned out to be 6, which was shorter than the previous minimum distance of infinity. So we made that update. So I'll go ahead and move up these distance and path matrices and make room for the very last distance matrix and path matrix. Okay, in this very last iteration, to update the distance matrix and path matrix, we'll ask ourselves if we can force ourselves to go through node D to find any shorter paths between all pairs of nodes. So to save a little time again, I'll go ahead and update both matrices, and I'll highlight the ones that had changes in red. So in this iteration, it turns out that there were no updates to be made to the distance matrix. So what this means is that this distance matrix 4 and path matrix 4, this is our final distance matrix and path matrix. So this distance matrix shows us the shortest path from each node to every other node in the graph. And we can use the path matrix to actually find the exact path. So for example, from node D to node A, the distance matrix says the shortest distance to get there is a distance of 6. Now to figure out how to get there, we use the path matrix. So it says to get from node D to node A, the most recent node that took us to A was node C. So if we write it out over here, if we're going from D to A, the most recent node that took us to A was C. So we'll say from C to A. But how did we get from D to C? Well, again, let's refer to the path matrix. So from D to C, the most recent node that took us to C was B. So B led us to C. But how did we get from D to B? Well, again, let's refer to the path matrix. So to get from D to B, it was a direct connection from D. So we went from D to B. So we'll draw a little arrow here. So this is the shortest path from D to A, and we know that that distance was a total of 6. So you can use the same reasoning to find the shortest distance from every node to every other node, and you can use the path matrix to figure out what path you actually took.